Hi everyone, my name is Łukasz Burdka, I'm from Techland, and today I'll be talking to you about open world streaming in Dying Light 2. To begin with, thank you all for coming to my talk. I know it's the last slot of the conference, so I kind of expected I'll be talking to empty walls, so I really appreciate that. Now, before we properly begin, please let me introduce myself so that you know who's talking to you. So I've been working in Techland for 8 years now. I worked on Dying Light the following, and Dying Light 2, of course. And I'm currently a lead technology programmer. I'm a part of the engine team. I'm developing our proprietary tech, the C engine. I'm mostly recognized for creating the City Builder toolkit, but I was also responsible for creating the world building pipeline that I'll be talking to you today. So the plan for this presentation is as follows. First, I will define what I mean by the term open world streaming. Then I will tell you a bit about the world of Dying Light 2, which will be the scene of our case study today. Based on those two informations, I will define the problem that we were trying to solve. Then I will show you our initial approach to open world streaming in Dying Light 2. And then I will tell you what didn't work and what we had to change in order to make it work in the final product. In the end, I will tell you what's like the takeaway for me, what are the most important lessons that we learned during this development. So I'll be talking about open world streaming, so it makes sense to first clarify this term so that we're on the same page. It can mean a lot of things for different people. Well, for me, it is how we load assets that are used in the game in order to deliver them to the player, but also how and when we unload them, and also how we handle transitions between loading and unloading the data and presenting it to the player. So it can be divided into separate sub-problems in our case. First, the load-unload thing, so how we load data from the disk to the memory, what data we load, when, how. Then, when we decide that we no longer need that data in the memory and we can free it. It's also how we spawn the hierarchy of world objects. So from the very high levels of the hierarchy to lower levels, and to the lowest details of our game object hierarchy. How we create them so that the amount of entities that are currently active is kept reasonable. Then how we camouflage those transitions by switching levels of details, called LODs in short. So yeah, how we mask the fact that we are loading or unloading something. And since it's also part of the performance task we're having, how we create those LODs and what are they in our world streaming scenario. Now let's have a look at the world of Dying Light 2. So we had two maps, but the prologue was like really small natural environment that didn't pose too much streaming challenge. So I will focus on the main map where the game takes part, which is the city. So our world, the city, it is a dense urban environment that's packed pretty tightly with content. We have trees and parkour opportunities on the rooftops, hordes of infected on the street, and quite a lot going on in between, so buildings that are also pretty detailed, and there's a lot going on there. Also, we have 5 distinctive playable regions, and I mean 5 in terms of asset management, because for players it could be more or less distinctive areas depending on how they perceive the game, but technically there were 5. So it was the Old Villador, which is like the low architecture, friendly neighborhood kind of map. We have small buildings, low verticality, it's a lot of nature and vegetation. Then there is Central Loop, which is a totally different story. We've got skyscrapers, modern architectures, a lot of verticality. They are both very close to each other. You can see the Central Loop when you're looking from the old Villador. Then there is the Cathedral Island, which has sacral buildings and also low architecture with sloping rooftops. So it is different building styles than old Villador. Then we have an abandoned electric car factory in the middle of a chemical wasteland. And also a sunken district that can be uncovered thanks to players' choices during the game, accompanied by a monumental pumping station. It's also an area that can be accessed. Also, our world features accessible interiors. So whenever you roam the map, you see interior locations that you can enter or underground locations. And those locations are available to the player without any loading screens. So it's all placed on one map, technically. It's also an FPP game, so we can expect assets in the game to have high detail and to be a lot of them, because players can really view them from a short distance. So it's just an example of such a place that is, you see, quite packed with assets. And it's accessible right from the outdoors, right from the street. It's the entrance to the Fish Eye Canteen in the Central Loop. So that's pretty much how the world looks like. Now it's also worth mentioning that the world, its structure, is created by our City Builder toolkit, which is like a 2D planner that we use to semi-procedurally generate the map. I won't go into too much details about it. I gave a detailed talk about it in Digital Dragons this year, so you can check this out if you're interested. But what's important here is that our map is divided into road segments, crossroads, and also areas that are covered with, filled with buildings, and also some unique locations in between them. And this structure of the world is enforced by this tool, by this City Builder. Okay, so now that you know a bit about the world of Dying Light 2 and what I mean by world streaming, let's define the problem that we are solving. So the problem is that we've got low-end consoles that pose some restraints, some constraints on us that we need to fit in the memory. All the time during the play, when the player plays our game, we must fit under memory budget. And also, the GPU and CPU time of a frame cannot exceed 33 milliseconds. Now, what makes this challenging is that prefabs, meshes, and textures all use up memory, and these are assets that our game demands all the time. Also, render items stress the GPU. Now, render items is a term used in our C engine. These are not really draw calls, you may know, because our rendering is optimized in such a way that draw calls were not a problem. But render items, you can think of them as just single instances of meshes that are placed on the scene that need to be processed anyway in order to be rendered somehow. And then there are, of course, logical objects, quite a lot of them, that stress the CPU because they need to be updated in each frame. Also, we want to make transitions between all those loadings and streaming objects unnoticeable, which also gives us a challenge. Now some numbers. We've got in our project around 1,200 megabytes of mesh memory used. Then about 4,000 megabytes of textures that we need to stream in. And 150 megabytes of prefab memory, which describe the structure of a scene. And about 1 million render items. And 700,000 logical objects, which are like entities that contain components inside. which can be understood as game objects. Now, what we can afford on low-end consoles is 600 megabytes for meshes, so half of what we have. 1,200 megabytes for texture streaming, that's a fixed buffer. So, well, you see. 50 megabytes limit for prefabs. 12,000 render items, not 1 million. 50,000 logical objects updated per frame. Of course, it depends how complex those objects are, but it's like 50,000 in average. So you can see the problem. We cannot just have all the assets we want at the same time. We need to somehow partition them and squeeze them onto the platform. So how we approach this problem? So the initial approach was something that was in development for several years. Then we had to change some things like in last 1 year because we ran into some problems. So first let's have a look at the memory. We handle memory problems using regions in our map. So as I mentioned, the map is divided into like 5 distinctive regions in terms of asset loading. So you can see here the map plan in City Builder. Now the red areas are regions, so they're like a partition created by level designers in order to group the parts of the map into streamed bundles. And yeah, I know, this sounds like a pretty obvious solution. So we have a map, so we partition it, and we will just load assets when player get there and unload them assets when player leaves. So the question might come in mind, what exactly happens when player traverses from one region to another? What happens in between? So that's why our regions are also separated by those special regions in between them called buffer zones. And buffer zones are meant to just use only like very generic assets, assets that are commonly used in the entire map. And when player crosses from one region to another, the buffer zone is always loaded at the time. So we keep loaded not only the region player is at, but also all of its surrounding buffer zones. Then, I hope you can see this, yeah. There's another layer on top of that, which is called region borders or region switch borders. There are those gray lines that you can see, and they define the exact place where the loading starts when player crosses from one region to another. So we have a full control of the process when we will start loading assets and when we unload the region we're leaving. So the way it works in details is when player tries to move from region A to region B, he always needs to cross a buffer region in between. So when he enters the buffer region, nothing happens. As the player crosses the blue line, region A unloads immediately. The buffer zone is, of course, still loaded, so the player shouldn't notice anything. Then the player, then we start loading region B, and it has to load before player reaches the border of region B. So, sounds good. Of course, there can be problems like what if player turns around in the middle and decides to come back, but then we will do like exactly the same thing. So cancel loading region B and start loading region A. So now we need to guarantee that player will reach it when it's loaded. So this imposes some important constraints on how the map should be built, right? We assumed that region loading from the technology side that we guarantee that they must load below 10 seconds. That's the time that level designers should guarantee we have from the border to the actual region and buildings inside. So we agreed on some player speeds. That is the maximum player speed that we cannot surpass. Then we agreed that the transitions between the regions will be executed in specific choke points, like bridges or tunnels, or places that we can easily test and control if we can make it on time. So I know it sounds pretty good, right? We agreed on something, nothing could go wrong, right? Spoiler, it didn't quite go the way I meant. So the region resources that we need to load when we cross the border are meshes, so the geometry of everything that will be used in that region. Prefabs, which are like the descriptors of the object hierarchy, and geometry data bundles, which is like a CEngine specific thing. It's just structures that optimize rendering of our meshes. They speed up rendering greatly, but also they take up memory, which is like a common trade-off in optimizing things. Now, when we enter a region and we load all assets that are used there, we also need to spawn the objects in the world so that we see them, because we couldn't just afford to have everything in the region created at once and displayed at the same time. So we have a system called spawners that are meant to create objects that are only near the player, destroy objects that are far away from the player, and also replace the destroyed objects with LOD. And when I mean objects, they can be many different things and many different hierarchy levels. I'll get to that in a moment. But our spawners also spawn and despawn certain spawn types of the geometry. So our geometry is always categorized so that it can be either exterior detail, interior or interior detail. And you can see the colorful overlay on the right. The green represents exterior, then the cyan is exterior detail, yellow for interior meshes, and then red for interior detail. So the idea is that as we move toward a building or an area, we first spawn the geometry that is most noticeable and largest, so the exterior, then goes the details, and then interior, like as close as 30 meters to an object. We have the spawn hierarchy, so the spawners form a hierarchy in our world. So first, the whole region spawns, but it doesn't spawn the geometry. It spawns just like logical areas that have their own spawners that create buildings, and those buildings then spawn building layers. So it forms like a spawner hierarchy. Only the ones that are near the player get spawned. And it was like that for most of the development, but near the end we actually resigned from the buildings level because it was like too many meshes for LODs and too many prefabs generated, so we just resigned from one level of this hierarchy, and the areas of buildings are now replaced by building layers, not skipping the buildings entirely. So it looks like that. That's the region from the bird eye view, or part of it. It's what's spawned first. Then we spawn a single area. The building level itself is omitted. And then we have building layers, which are like one story, or sometimes we compose them into a couple of stories. So our buildings are just composed of layers. So how spawning works. Every object or every hierarchy in our game has got an extend or axis-aligned bounding box, AABB, which is like the box that is the upper bound of the geometry inside. And if this extent of the spawner is 72 meters or closer to the player, it gets spawned, marked by green. If it's farther away than 72 meters, then it's replaced by LOD. And you can see that even if the spawner just touches slightly the 72 meters circle, it is spawned. That's how the system works. Of course, we have some hysteresis, like 2 meters, I think, so that if players move back and forth slightly, we don't experience the jittering in spawning. Now, I mentioned that we replace those objects with LODs. So what are our LODs? How are they created? LODs are sometimes in some systems called proxies. In our case, we didn't use any middleware for that in the final product. The way we create them is 3D artists create like a proxy meshes for our prefabs, like for this canopy here, for example. In this case, it's like one mesh for one mesh, but we can create like a representation, proxy representation for the bigger prefabs as well. So if on the left this model was created from, say, 4 or 6 different meshes, we could still create just one single proxy mesh for it. And then during the generation phase, like baking phase of our city, we gather all those proxy meshes that are under a spawner and group them together into a single mesh that will be used as LOD. And then we just bake the texture on top of that. So 3D artists don't prepare textures for LODs. That's something our engine does when the map is built. Then for regions, okay, so this is like a LOD1 created this way. LOD2, or the region LOD, is something different. We didn't have any cool automated way to do it. Instead, what we did was we took a scene created from LOD1s for the entire region, exported it to an FBX file, and then our 3D artist would just open it in Max, optimize it even more, like decimate some triangles, make it look good and be really optimal, because the region LOD is loaded at all time. It's like the horizon that's always visible. So these meshes had to be really lightweight. Then they also like bake a low resolution texture on top of that, and it's important back to the engine. And also in the engine, when we import it, we also merge it with the simplified terrain mesh that was used in this region before, because terrain is also something that we unload when we exit a region. Just replace it with a really simple representation with no collision hull, no trace hull, no stuff like that. Then there is the lots switching. So you know what our LOD is. Now what happens when we move farther away than 72 meters from something? Yeah, as I mentioned, it's a distance to AABB. So once we move further away than 72 meters to AABB of a spawner, it replaces it with the LOD. Now the entire spawn type of a, say, building floor is switched at once. So when we reach the exterior distance of the area, for example, we despawn all of its meshes and replace all of them with the exterior LOD. If we get like closer to 30 meters to a building, then we replace the LOD of the interior, which is usually just like a patch in the window, with the actual interior. And there's no division below that spawn level. We also use what's called a temporal dissolve to hide that. So when we switch LODs, we have like about half-second transition period when we display some pixels of the LOD and of the original geometry at the same time, and we like progressively display more and more pixels of the LOD. And then when all pixels of the original geometry are gone, it is destroyed. You can see the way it works on this old video, because as I mentioned, that's the like first iteration of the lot switching process. So you can see all those colorful meshes are like single render items that are being replaced by LOD geometry as we move further away. So it's like a single color represents a single mesh, more or less here. The colors are randomized, so, but well, you can see as the geometry noise increases when we get closer, it means that it is spawned. It's replaced by the original geometry, and the LOD is gone. You can also see this in the wireframe view. So we not only optimize the number of render items or draw calls, but of course also the triangle count. So as we move further away, you should be able to see that the wireframe gets much less dense. And as we get closer, it gets denser and denser. So that's like the really classical way of switching LODs, I think. To save up memory and some rendering power, we also have a technology called Tiny Objects. And Tiny Objects is like a dedicated system that is used for small vegetation and debris that is spawned around the player. These are objects that have no collision, must be simple geometry, so we have they cannot have skinning. They have some vertex limitations that they must follow. And we never save their positions. We just save like a 2D density maps of them that are in the world space. So we have like a low placement precision because the precision is like 1 meter per 1 meter, saying how dense tiny objects should be placed in that block. But it saves a lot of memory thanks to that. And also, we never store those positions or those objects. We just seed them in real time around the player as player traverses the map using ray tracing in real life to just decide where those tiny objects should be placed. So in this example, you can see the roof without tiny objects. There is some vegetation that had to be precisely placed there because it was very contextual. But then you can see tiny objects appearing. Those small plants. So that was like an additional system for streaming that helped us free up the memory. And it's like, I think, 60 meters around the player is the radius where they are created. Then we noticed that we still have a problem with mesh memory. And after analyzing what meshes are the heaviest, we figured out that the character meshes take up like the most memory, and also that some of them are very unique, meaning that they only are used in 1 or 2 places in a region. So we decided that it doesn't really make sense to load them together with the region data. Instead, we created a separate loading system for character meshes. Tomek Kosek did a talk about that on Digital Dragons, but just to overview this system, it works like that. When we need to spawn an AI character, we spawn it in a very simple LOD, which is like this guy on the right, which doesn't have any geometry at all. It's like just a sticky figure with some shader magic rendered like this. And then we start loading asynchronously the mesh from the disk that we need. And when the mesh is loaded, then it gets switched to the guy on the left. When we no longer need certain type of NPCs, we just free the mesh immediately. Texture streaming, because I also mentioned that textures take up memory, of course. It could be like a good talk for another short presentation, so I won't go into details now, but just to give you some principles about the system. So we have like a fixed memory buffer. It's platform dependent. On the low-end consoles, it was 1,200 megabytes. And when we load them up, we first preload like small MIP maps, miniatures of the textures that we first gathered as commonly used to make sure that most of the textures are already loaded ahead when we enter the map. And we are not stuck on the I/O of thousands of textures. Then when we see some object on in the viewport, we stream in the required MIP maps. So if the object is bigger on the screen, it needs to be higher quality texture loaded, and we prioritize in the I/O the ones that are like the most visible on the screen. And if we stream a texture and we no longer see the object, we still keep it in memory because, well, you know, we can like rotate the camera around and we would be constantly streaming in and out. That's something we really want to avoid. So we only unload textures that are unused when the budget is exceeded. So when we want to load something and there's no longer a place in the memory for that. Okay, so that's like the principle of our initial approach to word streaming in Dying Light 2. Now let's have a look at what didn't work and what we had to change. So we had three main problems. First one was with spawning regions and region borders. That was like the biggest pain we encountered. Another one was loading resources for unique locations, so like hubs, churches, locations that are only used once in the game, and they are also very important for the story. So they are like use mostly a lot of nice, beautiful assets that are very problematic for streaming. And also the way our LODs were switched and blended was not uniform because it was extents-based. So it heavily depended on what are the extents of objects in our game. Some locations like the metro station or the like peacekeeper's ship were enormous, while other like objects that we wanted to spawn or load were very small. And this strategy had a problem with that. So region borders, what's the problem? Well, as I mentioned, we trusted level artists and level designers to ensure that there's enough space between the region border and the actual geometry, and that the player will always be able to reach that place. But in practice, what we ended up with was players getting too close to region borders before it loads. So the players would see something like that, for example. And the reason for that is that the design changed in some ways. For example, we were meant to have like a toxic water between the central loop and the Cathedral Island so that the player can never traverse through the water, only through bridges. But, you know, designers figured out that it sucks and player needs to be able to traverse anywhere, so we changed that. Also, we introduced paraglider that allows you to fly from one district to another. And that paraglider featured upgrades like flying speed, which is twice as great as the player running speed. So, you know, Jiras and bugs started popping up, and we at Technology had to solve this somehow. So yeah, players can get too close to LOD. That's the problem. So how do we fix that? You know, we already have the map divided. We cannot really change the partition because the game is almost ready. So we need to figure out how to present region borders better. So we introduced a way to just mark the first line of buildings, or just whatever parts of the city you really want, to be in LOD1 quality. So we take those higher resolution LOD meshes and just use them in the region LOD instead of the geometry that's like ugly and low resolution textured. Of course, it also hit the memory a bit, but you know, it was acceptable from the player's point of view because the first line of buildings wasn't ugly anymore. But still, there were cases like with this paraglider when the player would still like traverse too fast and was even able to reach the like first building lines of LODs and just fall under the map because LODs don't have collisions. So we had to add areas around the regions with the please wait screen that is sometimes visible on consoles if player moved too fast and the region doesn't spawn on time, then we have to just forcefully block the player in place and display this. Now, unique locations. There were two problems with them. They were using unique asset, unique meshes, and also they featured really heavy interiors in terms of render items and logical objects. So because we spawn interiors also by distance, it means that if we were like close to a church wall, for example, we would still spawn the interior, which is inside with all NPCs and everything that's heavy, even though the player had no intention of entering the church actually, just because he was in the range of its extents. But the assets used exclusively by unique locations made like region bundles really heavier and expensive to load into memory. And interiors were just heavy. Right? So the way we solved this was we created like artificial regions that were added on top of the existing regions just for the unique locations. So every unique location could be assigned to this virtual region that doesn't unload anything when we enter it. It just loads additional data that is used only in this unique location. So what we gained this way was that, well, we at least had only assets from one unique location in region loaded. So if we had like 3 or 4 different hubs, we only loaded those additional assets for one of them, the one that player actually is near. The area where this region needs to be added had to be also handcrafted by designers. So we had to make sure that these unique locations will be able to stream in time. And also for the interiors and the problem that they had too many render items, the way we solved this was we added an additional sensor that was usually like covering only the actual interior location and some area before the entrance to the location. And only when player entered that sensor, the interior would spawn. Otherwise, it was despawned. So the problem that the player is like near the wall, doesn't intend to enter, was no longer a problem. Now, the LOD's blending is something that needed like, the greatest rework in whole this system I was talking about. And it's because big locations were using like way too many render items. So I mentioned like the Peacekeeper's ship or any big location. It's just enough for us to hit a fragment of extents of such location, and we were rendering it all, like with all of its details. So it was even worse because the extents of locations are calculated based on the objects that are inside. So if some level designer would make like a mistake and add a mesh to the hierarchy of the hub that is on the other side of the map, it would make the extents enormous, and then such a location would be like, rendered even though we're really far away because the system thinks that we are in its extents. So like this type of errors happened all the time, and we realized that it won't be probably possible to fix them all in the data, and that we need a system-wide approach for that. And lot rendering distances really varies in that system because from what I shown you, right? So we can see that those green areas that are in like original geometry, they can be rendered really far away from the player if only the extents are hit by that, which means that we cannot really expect any uniform distribution of render items across the scene. So the way we figured out to change it was we use the distance-based dissolve instead of the temporal one. So what it means is that the geometry that's up to 72 meters to the player is always like the original geometry, and everything that's exactly farther away than 72 meters is LOD. So I will show you in a moment how we achieved it. This gave us the like great advantage that we can implement culling objects that are farther away, that's 72 meters, so we can not render entire meshes that are farther away. We can even cull single triangles in the shaders that are further away from that, if we have like big meshes, and we know that some of their triangles are entirely further away than 72 meters, we can call them. And this way we really lowered the stress on the GPU in terms of triangles and render items. But it required us to render both LOD geometry and the original geometry at the same time, and just do the very smart blending by distance at 72 meters range, so that the LOD geometry is never seen closer than 72 meters, even though technically it's rendered, but we hide it in the shader. So in this video you can see how it works in the game actually right now. It's in the editor, so the quality is lower, just to make it more visible. So when we move further away from the buildings, you can see this dissolve pattern on the windows that was there for a moment. And what we see right now is the LOD of that. When we move closer away, that's the moment when it changes. When we move closer, now it's the original geometry. So at the same time, we render the LOD and the original geometry of that building. And based on the 72 meter sphere, we just blend them together. So when I disable the LOD rendering right now, and just show you how we render the original geometry, it will be more visible. So as we move further away now, there are no LODs, so you can see that the building is disappearing at the 72 meters sphere with this dissolve pattern. And when it's not replaced by LOD, of course, it just disappears. But there should be LOD, and there are for everything in our game. So it was like a really efficient way of rendering things. Of course, the important problem with that was that the LODs had to be done really well and really match the original geometry, because otherwise this blending would be quite visible, and we didn't want that. Okay, so what do we learn from all of that development process? Of course, it's such a broad subject that it's difficult to summarize it in a simple way. But here are some of my takeaway points. So it's difficult to design a system or spawning streaming system without the data that's in the game. So, perfectly you would first have a game world and then create a technology to stream it, but of course it's never possible, especially if you develop the technology alongside with the game. So you always have to keep in mind that as the data in the game, as the map grows bigger, you will hit challenges that were unforeseen before. Then the spatial separation of assets is important, which means that it would be best to just use assets locally. If you use some architecture style, don't use it anywhere else. Our problem, and the reason why the regions had to be so big, was because every mesh was used everywhere else, and we had assets really blend together. Of course, we had those major architecture style, but other than that, we couldn't really benefit from more dense subdivision of the space, because inside the region, all sub-districts were using the same assets. And that doesn't leave too much space for optimization. Also, guidelines for map creators, level artists, level designers, they are not followed. You should be aware of that and should be ready or somehow try to enforce them. But generally, the system should work without assumptions that the map will be created in some specific way, that you will have enough space, enough time you want. Also, HDD read time is a real pain, and it's the most disappointing feature of the hardware, I think. The biggest problem was when we were trying to read a lot of small files, or even one file, but a lot of 6 and reads in that. For example, when we were optimizing textures, at some point we were downscaling the textures, really making a lot of small textures to keep the total memory amount low, and it sounded great because like the numbers in our streaming budget were great. We were like half the capacity all the time, but because of how many little textures we had to read from the disk, it could take like 10 or 20 seconds for the textures in view to stream in on low-end consoles, which was like horrible. So we had to like optimize again in terms of read times, not really memory. So I'm really glad the new-gen consoles are no longer using them. Also, the open world streaming, well, it can work quite well if constraints are followed, and it actually allows us to pack quite a lot of content and make the performance of the game almost independent from the scale and size of the map, if it's only following some basic guidelines. Thank you very much. I believe we still have time for questions.
Thank you for the talk. I have a couple of questions. So, in the first part of the talk, you mentioned that you have those streaming regions, and between them there are like those transition regions where, correct me if I'm wrong, because this is important for the question, where, if I understood correctly, they were only the objects that would be permanently in the memory, kind of like universal meshes, so you can always render those transition regions, correct?
Yeah, almost. I mean, when you're in the region, all of its surrounding special regions, buffer zones, are rendered. So if you have like a larger area, and the buffer zones that are not touching your regions, they are not loaded.
Okay, so didn't that put like limitations on the environment art, basically, on where they could
yes.
put, and how did you handle their unhappiness?
So this was one of those things that we just said they cannot do, and there's nothing we can do about that. So they cannot, for example, mix architecture styles between them and use anything inside. And it was like a real problem because we wanted to like enlarge those buffer zones at some point, because like we needed to make it bigger between the central loop and the cathedral island, but we couldn't because just increasing its size would mean that they are buildings from one on or another style, and they will be in memory all the time, and we couldn't afford that. So it was like something that was a really hard constraint. And we just said to level artists it had to be this way because consoles.
Okay, thank you. And then the other question, if I understood correctly, like for the LODs, you were at some point, like you were using like manual LODs by artists, right? Have you considered using the nanite-like approach based like on this graph cuts for the meshes, basically like automatizing LOD generation like they do in UE5?
You know, when we designed the stack, I think nanites were not such a big thing, or not even publicly available as a common knowledge, so we didn't. But you know, I think we already had the LOD creation pipeline in place at that point. It was quite efficient, actually. So of course, it could be automized, could be done better, but we just wanted to have like full control of the LOD's quality and what they look like, and yeah. So I guess it could be automated. To answer your question, we just didn't consider it at the point. I mean, we were using our own in-house solution at some point. It was like a voxel-based LOD generation, but it just wasn't good enough for the production quality. We're just using it for like a prototyping and to have anything in the scene so that objects don't disappear.
Understood. Thanks again for your presentation and for your answers.
Thank you.
How did you address the problem of fragmentation?
Okay, so the question is fragmentation. Fragmentation was a problem for meshes and mesh bundles mostly. Because for textures, as I mentioned, we have like one fixed buffer for that. So it's allocated just once. And for the meshes, you know, the problem wasn't so great because when we enter like one region and we load all assets that will be used there, and when we leave that region, we just unload them all. So we free and load like big chunks of memory. It's partially fixed this problem, but I think there was a point where you would just, when you traveled alone, just using a free camera between regions and the spawning and despawning them, that the fragmentation was increasing. We didn't handle it in any special way. We just had like some margin, some buffer in the memory that we assumed that the fragmentation can go up. But it wasn't too much of a problem in practice because of how we bundle the data that we load. Not loading small files in general. That was, no more questions. Thank you very much.